Hello. I think I was zoning out. Looks like it's time to get started. Welcome back, everyone. Looks like it's just us four folks today, but we'll still have a great time, I think. Hopefully, we get some more in Zoom. Any questions folks would like to discuss to start us out today? The burning linear algebra questions or things of that nature? Okay, well, for our quick rundown of the announcements, we did make a start on section 4.5, but we didn't do anything too major there. We'll go over that first example that we finished on Tuesday's class. Then, after finishing section 4.5, congratulations, you've gotten through the toughest chapter of linear algebra, I'd say, section 4.1 being the worst offender. Section 5.1 is now going to be direct applications of essentially everything we've done in chapters 1, 2, 3, and 4. So we're starting to combine a lot of techniques. We'll have to do things like understanding spanning, linear independence, row reduction, determinants, and issues with dimensionality, null spaces. All of that comes into section 5.1. Well, eigenvectors and eigenvalues, that's a mathematical application. But this one concept right here is one of the major reasons that linear algebra just has its hands in just about anything. Even if you're in Calculus 3 studying a multivariable function, maybe it's from an application, those are hard to work with, but oftentimes what we do is we linearize it. Take a look at the eigenvalues, eigenvectors, and study the linearized function. So this is now getting really close to some of the honest applications you would be dealing with in engineering, chemistry, physics, and all sorts of great stuff. But we'll make a pretty good headway in section 5.1, section 5.2 before the exam. But I'm thinking of making the exam end on section 4.5. I think that's a natural stopping point for that exam, mainly because 5.1 is going to be covered next week. And that's not a very long turnaround for you all to practice those problems there. Before we get to Tuesday's class on April 9th, I'm going to try to do it as soon as possible, but I feel like this is a good final deadline. It's a busy week. Before getting to the next Tuesday's class, I should have information here for the exact coverage we're mentioning and the review problems that you typically expect. But that's our announcement so far. And if we move to here, let's take a look at what's going on. We'll be doing sections 5.1, 5.2, potentially 5.3 in this week. Then here we'll be finishing off chapter 5, looking into as many applications as we can get into in chapter 6. And then finally this week down below, on Thursday, let's see here, April 20, let me see if I can get those dates right. Yeah, this one, April 25th, that'll be our day to review for the final exam. So no matter where we end up, we'll take that whole day to review. The sample final exam problems are already posted there. And these are the same ones that I've been mentioning that you could take a look at for exam 1, exam 2, as well as the upcoming exam 3. It's a pretty huge document, so you may not want to print out the whole thing. And it targets section by section interesting problems just to be aware, with solutions at the very end. But I'll be posting some additional problems as well. How do I close this tab? There it is. But before we get to that date, getting closer to the final exam. Well, excuse me. Well, this is where we're at so far. Any last questions at all, folks, before we jump back into 4.5? Okay, it's an exciting section. We've been kind of hinting at it since section 1.3. We're discussing how all the definitions stack together. So now finally at this point, well, let's maybe pause right here first and mention some issues. The definition for the dimension of vector space looks simple on the first glance. You want H to be spanned by some finite set. A finite list of vectors should span it, and they'd be independent to form a basis. Then once you have that basis, dimension of H is just the number of vectors in a basis. So it doesn't sound too bad, but it's actually a pretty technical definition. The things that we haven't mentioned here is you can put down a vector space like this one. This is the vector space that contains nothing but the zero vector. And let's consider how weird that is. If you have nothing but the zero vector here, well, the set containing the zero vector is linearly dependent right away as a concept. I mean, the zero vector itself is linearly dependent. add it to any set of vectors, and it's a linearly dependent set. It's like anything that the zero vector touches causes dependence automatically. But now, looking at the definition for a basis, you need two things. You need to be able to span this set, and that works. Span the zero vector, you only get back the zero vector, but you also need a linearly independent set. There is no linearly independent set that spans H. And so this is an example of a vector space that has no basis. So now the definition of what we mean by dimension is starting to get complicated. If this one has no basis, it seems kind of natural to say it's dimension 0. And that's the definition we're going to take. The trivial subspace is of dimension 0. But there's even more weird things going on because some vector spaces, even though they're not the trivial space, you still cannot span it with a finite basis. You need an infinitely long basis, and that's going to cause other issues. We might call those infinite dimensional vector spaces, and that's exactly the route linear algebra decides to go into. What it tells us is the definition for dimension really has 3 different cases, so it splits into 3 categories, and we have to carefully track through all of them. But even worse than that, when we say for the best situation, H is spanned by a finite set, so not a zero vector situation, so we have our honest vector space. The dimension of H is the number of vectors in a basis for H. We have a massive problem just right there in mathematics. And this is a problem of something being well defined or not. If that's a real definition, we now have to say, how do we know every single basis would have the same number of vectors? For example, if you found a basis for H with 2 vectors, you'd call it dimension 2. But now you have to justify where there can never be a basis of 3 vectors or 1 vector. And that's where section 4.5 starts to talk about. It's trying to give us something well defined for the concept of dimension. And this is the first theorem that gets us there. Theorem 9 says, if you found a basis for a vector space V, and you found that it contained n vectors, this is an interesting proof that you could read through if you have time, but the punchline says, any set in V containing more than n vectors is now linearly dependent. Not quite the definition or theorem that we want. We want a theorem that says every basis has exactly 9 vectors. But this is the first step in that direction. It also allows us to compute things really, really fast. For example, the moment we put down a standard basis for P2 with 3 vectors, we know automatically that's linearly dependent because it had 4 vectors. So that's theorem 9 in action. So now getting a step closer to defining dimension, here's the real theorem that we want. Theorem 10 allows you to write dimension as a function, which is truly well defined, as long as you're careful with the fringe cases. It says, if a vector space of V has a basis of n vectors, then every single basis of V also has n vectors. So that number is intrinsic somehow to the vector space V itself. So back in this land, if you were ever seeing a question on exam 3 or the final exam to give a basis for R4, you have a lot of different options. You might go E1, E2, E3, E4, giving the standard basis. Or some people might get creative. Let's do a creative one. A basis for R4 could look like this. 1, 0, 0, 0. Now that one is E1, but let's make this one different. 1, 1, 0, 0. 1, 1, 1, 0. And the last one is going to be 1, 1, 1, 1. That's definitely a basis. If you put all of these into a matrix, so the columns correspond to each one of these vectors, the determinant would be the product of the main diagonal, which is 1. And then the invertible matrix theorem would tell us, well, let's take a look. The determinant would not be 0, it'd be 1 for that matrix. And that tells us automatically, let's see here. I skipped over it. There it is. You have a basis the moment you know you do not have a 0 determinant. So we did it, folks. We wrote down a basis. And the thing that we want to take away from this is that this has 4 vectors. So now part B asks us, explain why this set cannot be a basis. those vectors are possibly linearly independent. Row reduction can help us see that, but it cannot be a basis for R4 for multiple reasons. Now, if you're thinking of theorem 4 in chapter 1, I'd say that's a good way to think about it. If you put those three vectors into a matrix A, there's no way there's a pivot in every single row, not enough columns to make that happen. But you could even argue slightly differently by saying B has only three vectors. And so, let's just put a disclaimer here by part A. And theorem 10. It is not a basis. So the issue is right here. It only had three vectors, and we found a basis for R4 containing four vectors. This is insufficient. It needs more vectors in order to form a basis out of what we had so far. So kind of nice to know you have options for answering these kinds of questions about linear dependence. This is essentially a spanning question. There's too few vectors to span all of R4, but it's also good to think of it in terms of theorem 10. Our whole goal about this is, now that we know every basis contains exactly n vectors, we can write down a function. It'll look about like this. Dim for dimension. Function needs an input, so this is very much like function notation. Give it R4. Observe you found a basis with four vectors. And so the dimension is 4 right away. So already that was a problem. It's just too few vectors. We need exactly 4 to form a basis. Well, any questions, folks, with this example 2?
If you have 5, it's not going to be, it is not going to form a basis.
Exactly. If you had 5 vectors, you would go up here with theorem 9 and say, well, the moment we found a basis with 4 vectors, 5 is linearly dependent, so not a basis. So theorem 9, it answers dependence or independence. And theorem 10 is really a theorem about spanning as well. Other questions or comments so far? Okay, well, let's keep on going. Here's our big definition. I put here just as a reminder that this was one of the major things that we're trying to achieve in a linear algebra class, getting to this point. And once you have a good working knowledge on dimension, that's when things like eigenvalues and eigenvectors are most easily understood. And that's a source of most applications in linear algebra. So let's put down some examples as we go through this. It says, if V is spanned by a finite set, then V is said to be finite dimensional, and the dimension of V, written as dmV as we did before, is simply the number of vectors in a basis for V. So let's put down an example to illustrate. We put down, say, H equals, we want it to be spanned by a finite set. So we might say H equals span. Let's make it be 1, 0, 3. 0, 0, negative 8, so just a random set that we're spanning, 2 vectors. But automatically we can say, well, let's span by a finite set, exactly 2 vectors. And those vectors are not multiples of each other. You can tell already from row 1, if you go from 0 to 1, then they're absolutely non-multiples. So they're also linearly independent at the same time, no row reduction necessary. So this tells us that H is finite dimensional. We can just simply observe that's a basis. It spans. We did that by definition of H. It's the result there. That gives us, by theorem 1 in chapter 4, a real honest subspace of R3. And we know that they're linearly independent. So we can now say right here, dimension of H, number of vectors in a basis, which would be 2. So this is the typical example. This is the one we're going to be working with the most. But there are also fringe cases we have to take a look at and understand as well. So that's the next portions down below. Any questions, folks, with that first example there? Okay, this is the weird one, the zero vector space, sometimes called the trivial vector space, like we called it in section 4.1. It's designated this way, just the one vector goes in there. And it says the dimension is defined to be 0, kind of like what we mentioned before. But what I want to do on this example is illustrate how this could come up, how it will come up in the upcoming homework assignment for this section. It'll be something along these lines. Let's put down a nice matrix. Let A be equal to 1, 0, 1, 3. This is a nice matrix because the columns are invertible on this thing. Or the columns are invertible. Let me say this differently. The columns are linearly independent, and so the matrix is invertible. It's good to say those things correctly. So that's our matrix A. Now we can say next that AX equals the 0 vector has only the trivial solution. Why is that? Well, if the columns are linearly independent, then that means there's a pivot in every column. That means there's no free variable whatsoever in this matrix equation. And so the only solution you could put in there for X is the trivial solution, referring to the 0 vector. Now, what does this all tell us? This means that null A, which is the set of all solutions to that equation right there, equals the 0 vector, which then implies, and let's put that in blue just to say, that's what we meant by the trivial solution, that 0 vector. This implies that the dimension of the null space of A is 0 by the definition right up here. So that's the way this part right here is going to come up in the homework problems, potential exam questions as well. Any questions about that portion there, folks? Okay, it's absolutely a fringe case when we think about it, because when we say that our definition for dimension is the number of vectors in a basis for V, well, that just depends on what your vector space is. Always a good reminder, that has no basis. The 0 vector is linearly dependent by nature. So now it takes us to the really weird examples. We like finite dimensional vector spaces because with our work on isomorphisms, you can say stuff along these lines. Maybe just jam it right here. If the dimension of V is n, so we have a finite dimensional vector space, then V is isomorphic to Rn. And we've applied this fact quite a bit already in section 4.4. We'll do it again in these notes as well, because it's a good problem to come back to, and also because it's assigned in the homework. So it tells us that no matter how crazy your vector space V is, maybe it's a polynomial space or worse, if it's a finite dimension n, you're really just operating in Rn. And we use the coordinate mapping to actually do all the linear algebra right there in Rn itself. So what's going on with the infinite dimensional vector spaces? These are the really, really weird ones. And once you have two infinite dimensional vector spaces, they are not necessarily isomorphic. They can be absolutely different. So this is an interesting branch of linear algebra that if you decide you want to take lots of math, you'd want to go into something called functional analysis, which really hits these issues here. But here's one space that has all of those problems. P, or another candidate would be CAB. To remind ourselves of what those are, you can double check section 4.1 for a better description. But P is the space of all polynomials, whether they're of degree 12, 12 million, they just have to have finite degree. So every polynomial is inside there. This is this vector space of all continuous functions defined on a closed set from A to B. Or we could do a vector space of all continuous functions whose domain is the real number line. That's an honest vector space as well. These are all infinite dimensional, which means these are the really, really weird vector spaces. You might think this one's not too weird. It's a polynomial space, but consider functions like this one. E to the x, that's absolutely a continuous function. It's defined on the entire real number line, so it belongs to CR. But if you're thinking in terms of polynomials, as well as power series, say the Maclaurin series for e to the x, if you're taking Calc 2, this is nothing but the summation as n goes from 0 to infinity. Let me know if I misremember this. X to the power of n divided by n factorial. Those are just polynomials, but that's an infinitely long sequence of polynomials being added together. So something inside here can be well approximated by polynomials inside here, and that's a pretty mad fact to think about sometimes. So there's a lot of interesting interplay with linear algebra, calculus 2, calculus 3, and just about any mathematical topic that you get into. Linear algebra always just seems to get its foot in the door. It's kind of amazing. So this is the weird stuff. We're going to take a look at it in the notes if we have additional time. But I want to be honest, this is something we like to talk about in linear algebra, but we don't have an opportunity to do a whole lot of problems on this kind of stuff. So if we have time, on the very bottom of the notes, we'll try to address why this is really infinite dimensional, which then shows us that this space is infinite dimensional as well. But before getting to all that, we just mostly need to be aware that there are some really, really bizarre vector spaces that happen to be infinite dimensional. And whenever that comes up, we just simply write down dimension P infinity as a shorthand to say it's infinite dimensional. Well, that's a big, long definition. Any questions, folks, with what we've written down so far? Okay, now let's give it a try. It says, for example, 3 part A, find the basis for H. I feel like we should probably put this on a new page. Let's just drop it down. We want to find a basis for this space here, H. It looks kind of gnarly, but we'll get through it. Then once we find the basis, we can determine the dimension right away. So to get started on this thing, really it's not anything essentially new in linear algebra that we haven't done. The very first thing you'd want to do to H is write it as the span of some set. So I always take an additional step here to explain how to get there. But you can take a shortcut on this first thing I'm about to write, because we've done it quite a lot, I'd say. This is the result of scalar multiplications and vector additions. So we want to unwind all that. First, think of this as a result that is essentially about to be put in parametric vector form. You take the coefficient A to start, pull coefficients to produce a constant vector, 3, 0, -7, -3. Those are all the coefficients of A, and then just rinse and repeat. Next value, next parameter would be B. Its coefficients are 0, -1, 6, 0. And last but not least, C has coefficients here going 6, -1, -8, and -6. Provided I didn't miscopy anything. Only requirement is that A, B, C be real numbers in R. And the moment we've written this, well, we've just spanned something. So this is equal to the span of those 3 vectors, 3, 0, -7, -3, 0, -1, 6, 0. And finally, 6, -1, -8, -6. So we've got it, folks. That's our spanning set there. Any questions so far to that stage? Okay, I want to tell you about the most common mistake when it comes to this problem right here. I've made this mistake myself as a linear algebra student to actually scan all my homework. It's kind of weird, but I know I've made this mistake before in the past. The dimension is not necessarily 3. Once you get to this step, remember you need a basis, and a basis does 2 things. A basis is a spanning set. We've got that. But we might have to pare it down until we get only the linearly independent vectors. So that's where we go and take a matrix A, fill it out with those same columns. 3, 0, -7, -3. A lot of copying on this one. 0, -1, 6, 0, 6, -1, -8, -6. And if we row reduce this matrix, the pivot columns of this matrix are the columns of this spanning set that are linearly independent. So we can delete anything that doesn't correspond to a pivot column and still have the right spanning set. So let's do our row reduction. I would not want to, well, let me take that back. Yeah, we could divide this one by 3 to get it started. I was thinking there'd be issues with fractions. Let's divide that. So we'll have a 1, 0, 2. And then more copying. Okay, so we've got it down. Now we can really start in earnest. So 1, 0, 2 for row 1. Row 2 we can copy, 0, -1, -1. Now I'll multiply row 1 by 7, add to row 3 to get 0, 6, 14 minus 8. So we're going to get altogether 6 as well. Then take 3 times row 1, add to row 4. And this will turn into just 0, 0, 0. Now, if you were doing this by hand on paper, observe right here that the 6s are just gone. You're taking 6 times row 2, adding to row 3 to produce zeros. Definitely a good shortcut to take. I usually don't do that because I am pretty sure that would make the notes really hard to read. So I'll take the additional step. But I mention that kind of stuff all the time because if you feel like you're doing busy work, doing as much copying as I am, you don't have to. You are welcome to take as many shortcuts as you see in there. So now I'm taking 6 times this, adding to the entries below, and that means everything else is 0. But now we have to remind ourselves, what did we want out of all of this? We wanted the pivot columns. There's a pivot here and here, and that means this column and this column, or if you're looking up here, those 2 columns forms the basis. Let's take that back. B equals 3, 0, -7, -3, 0, -1, 6, 0, forms a basis for H. So the idea is, essentially, once you find the column that's linearly dependent, that was this one, delete it and it still spans. So that's a wonderful theorem that we applied in the prior sections. That means if it still spans, and this is linearly independent, that's a true basis. So we did a whole bunch of work, and this is finally the punchline. Any volunteers to state the dimension of H? Exactly, we've got 2 vectors in the basis, so its dimension is 2 right away. But again, notice how dangerous this problem is. Just because there's 3 columns does not imply whatsoever dimension is 3. We have to eliminate the dependent column to have a true basis. Well, any questions at all, folks, on getting through that one? Okay, so this one's not so bad. This is essentially just a column space. If you decide to think of it in those terms, this is equal to the column space of A. And notice when it came to getting the dimension of what is truly just the column space of A, all you had to do is find the pivot columns. That's the shortcut on this. The moment you found 2 pivots, it implies dimension 2 just immediately. That turns out to be a theorem that we're going to state shortly. But before we go to that, there's a different kind of problem that we need to take a really close look at. When you go to take a look at the homework problems, sometimes your sets look like this. Other times, it looks way more confusing, like this set here. It could be even worse. For example, I think our author actually writes it out this way. So in the text, this is written as, goes over here and puts in A, B, C, D. I think the editor for this textbook just said there's too much space being taken up on that section, so they saved a lot of space putting them sideways. So these are really the same kind of set, but when I rate them out as exam questions, I tend to go this way. This is how we're used to working with linear algebra. But if you see something like this, you have a totally different kind of problem. I mean, it's similar, but not exactly the same. So let's show how to get through this one. First, all the information that seems interesting is on the right-hand side. A, B, C, and D are just arbitrary real numbers, but they have to satisfy this equation right here. So let's start off by saying H equals the sets of all vectors A, B, C, D, such that what I would want to do right away is just put this equation in a format we're used to dealing with. So add 3D to both sides to get A plus 2B plus 3, let's give it a little bit of space before the 3D, equals 0. So that handles the first equation. This one subtracts D from both sides. C minus D equals 0. And this one's ready to go. Let's just drop it in, negative C plus D equals 0. So that's our setup so far. When you look at all this, notice you're dealing with a homogeneous system. If you have a homogeneous system of equations, that means you're not looking at the column space of some matrix like we were in the last problem. We're looking at the null space. So we can say that H is equal to the null space of A where A equals, now we're going back to the same thing as we did before. Take the system of equations and just pull coefficients. For the A values, we have, let's see, 1, 0, 0. 3 entries because we have 3 equations altogether. We have 4 variables, so we're expecting 4 columns. So now for variable B, we go 2, 0, 0. For variable C, it's 1, or excuse me, 0, 1, negative 1. For D, we have negative 3, excuse me, positive 3, negative 1, positive 1. Coefficients are hard today for me for some reason. And that's the matrix A. So this whole set, it looks mysterious to start. Looks even more mysterious in the homework because of the way they go sideways with that vector. But it's just a null space of A that we've been looking at all along. So, well, if we want to compute null space of A, all we need to do now is solve AX equals 0, where that's the 0 vector. And how do we solve that? Well, kind of just a big rundown of what we did in chapter 1 for parametric vector form. Once we were working with homogeneous systems, we take the matrix A, augment it with the 0 vector, and row reduce all the way to reduced echelon form. So we want to get this as reduced as possible. We'll start a reduction right away. I'm going to augment it on the 0 vector, but it's a lot of copying, and we know nothing changes on the right-hand side for the 0 vector. So let's just start with our row operations right here and now. I'm going to copy in row 1 and augment as well. 1, 2, 0, 3. And here's the 0 vector right here being augmented in. Now let's do some row operations. Don't have to do anything to that row, so it copies in 0, 0, 1, negative 1. Then we'll add row 2 to row 3, replacing row 3 to get 0, 0, 0, 0. At this stage, it's done. This is in row reduced echelon form. And some of the row reduction does become pretty fast in this section because we're trying to emphasize the concepts a little bit more than just a bunch of row operations. So sometimes it goes pretty quick. Now let's see what happens here. We have a pivot column here, a pivot column here. And so now, just like we did above, we found the dimension of H was 2 once we saw what the pivot columns were, but this one's a little bit different. The connection that we have to make once we go down to part B, the dimension of H, is if H is a null space, we're more interested in the number of free variables. I'll just say free here for short. That's where the free variables would be. The original variables were A, B, C, D, but these are essentially dummy variables. You could change it to X1, X2, X3, X4, do the corresponding changes here, and you get the same exact set of solutions. Because of that, I'd probably call this X1, X2, X3, X4. The algebra just feels more familiar if we solve in this way. So now for the solution set to AX equals 0, we have that x equals, well, let's go slowly and start by saying x1 equals, on this row, it's going to be negative 2x2 minus 3x4. Next, x2 is free, so we just write in x2 is x2. x3 we can solve. x3 is going to be equal to x4. And finally, x4 is free, so we'll write x4, also x4. So just about there, folks. Now to get the solution set to AX equals 0, we use what we produced here and just build out x. We can now say x equals, put in x2, pull coefficients, negative 2, 1, 0, 0, plus x4, pull the x4 coefficients, they are negative 3, 0, 1, and 1. And I always encourage you to write down this statement. Every time you're doing a homogeneous system or building out a null space, you produce these vectors as just part of the process. But a good call is to write this next, where x2, x4 are in R. At this stage of the course, we have a good answer of why I kept on encouraging you to definitely write this down. It helps. The reason why it helps is we can now go back up here and say H equals null A for sure, but null A can now be expressed as the span of negative 2, 1, 0, 0, negative 3, 0, 1, 1. So that's kind of nice, because if we want to find the dimension of H, we need to establish spanning and linear independence all at the same time. We've got spanning, there it is. So that's kind of nice. The process just produces a spanning set. And here's an awesome fact about this whole process. We're going to mention this a lot in chapter 5. Every time you go to solve for a null space, the vectors that you produce here, which corresponds to free variables, are always linearly independent. It's never a coincidence. That's now a mathematical fact. We have two vectors here, so it's fast to check their independence from just this row here. Going from a 0, 1 establishes that independence. But even if it was 12 vectors, that would have been a long problem. If you follow this process and you've got 12 vectors there, you don't have to do anything further to check. You don't have to do like up here and really row reduce to find what the pivot columns are. They are always, as a guarantee, linearly independent. And that's so important, so we'll mention it again, but let's mention it here as well before chapter 5. The process of building null A always produces linearly independent vectors. It's a long statement once you go to write it down, but it's an important statement, so it's worth taking that time. Well, any questions, folks, to this stage?
Just all the vectors are independent, not the.
Exactly, just the vectors right here. And I'm really glad you mentioned that, because when you go to take a look at the homework problems, I did write down something here just to be careful with problems 1, 6, and 8. It says we must explicitly write down the actual basis. That's what part of the exercises are for those exercises 1, 6, and 8. But like you were mentioning, Rajab, we need to be a little bit careful. When we give a basis, we can't put span in front of those vectors, because the fact that you have span right here, that means this entire set is linearly dependent. Linear independence is just the two vectors, but spanning them produces infinitely many different vectors. So that's the wording in that upcoming exercises. We need to now say here, our conclusion actually goes this way. It's a lot of copying, sorry about that. Let's do this once more. B, which is equal to negative 2, 1, 0, 0, comma, negative 3, 0, 1, 1, forms a basis for null A. Deserves an exclamation mark because this one's a little bit more work. We actually have to solve a system completely, generate the general solution here, write it down as a spanning set, so we know we have a basis. Then finally, well, this is the punchline, dimension H, number of vectors in a basis, and we found 2. So the conclusion is always just really wrapping up and saying what you see right here. But this is an interesting concept. The fact that we found 2 free variables and the fact that the dimension is 2, not a coincidence either. We can say that the dimension of null A as a shortcut is equal to the number of free variables in that homogeneous system, AX set to the 0 vector. So actually, the moment you find these 2, you're done. The dimension's 2, and the whole process is ended. The homework is asking us to do a little bit further. The homework actually wants us to find the basis. But you know what? That's a good idea, because in chapter 5, you have to do exactly that. We'll later call these eigenvectors, for example, if we're reducing the right system. Eigenvectors are all about finding a null space, so this is actually well worth doing. Any other questions or comments, folks, with this conclusion here? Okay, so after dealing with what's essentially a column space, and this one, which is essentially a null space, the observations that we were making are these 2 right here. The dimension of a null space of A is simply the number of free variables in AX equals 0. Let me put that one in bold. I'm trying to make this more obviously a 0 vector. Sometimes that sneaks out of my notes, but I've always tried to make it bold if I catch it. Likewise, the dimension of the column space of A is the number of pivot columns in A. And out of all of this, you have to actually be a little bit careful. Let me show you why, what's going on with this. When it says the number of free variables, we're thinking among the columns of A. I mean, that's where you look. You row reduce A. Let's take a look here. Look amongst the columns of A and find which ones are non-pivot columns. That's the free variables. Now, the one down below says the dimension of the column space of A is the number of pivot columns of A. I mean, that's definitely talking about columns as well. It's a little bit more descriptive there when it mentions that. So this tells us if we go to use this theorem and you know your matrix A is of size 5 by 4, what's most relevant is the columns, not the number of rows. It could have loads and loads of rows, but that's totally irrelevant to this theorem. You're more interested in the columns. Let's put a note here. The theorem above is all about columns. So example 5 is kind of a quick problem just to think of that idea. Example 6, another quick problem, same kind of idea. It says A is of size 5 by 4. AX equals 0 has exactly 2 free variables. So I want to go for blue on that. I'll just hit it with this. So we want to state the dimension of the null space, the dimension of the column space. But the moment they say that, they gave us half the answer. We can say dimension of the null space of the matrix A is 2 because of the 2 free variables. So that's kind of nice. Now we want the dimension of the column space of A. And to do that, here's the file I would probably always try to have. Dim for dimension, col for column space of A will be equal to, you definitely want to start right here. Whatever this is, take 4 minus your prior answer, because those will have to always sum up to the right value, the number of columns. In other words, this is simply the observation that the number of pivot columns and the number of free variables adds up to the total number of columns in your matrix A. So this one turns out to be 2 as well. Well, any questions, folks, with that concept question there? Kind of nice. You don't even need to reduce anything about this matrix. The moment you had that information, you're all set. Let's do it again down below here, just for the sake, I mean, it's the next problem, we ought to do it. let's see how this one's going to go. So based on our prior discussion, when you go to think of this, you want to know the size of the matrix. This one is 4 by, let me double check, 1, 2, 3, 4, 5, 6, 7. But it's the number of columns that's of most importance, 7 altogether. Next thing we want to do if we're looking for dimension null, column space of A, we need to find the pivot columns. We have a pivot here, 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 and here. So those are the pivot columns altogether. Now we're pretty much done at this stage. We can say dimension, column space of A, by the definition of above, is the number of pivot columns. And so this would be equal to 4, just by observing where the pivots lay for A. That means dimension of the null space of A. Anyone see what this ought to come out as? Absolutely. You could count them by just the free variables here, or just take 4 away from 7, and either way, you've got it, dimension 3. Well, this is a nice matrix. We didn't have to do any row reduction whatsoever on that kind of thing. And these make some pretty good concept style questions, either on the third exam or even potentially the final exam. So these are good things to come back to. Well, any questions, folks, so far? Getting through these examples kind of fast. Let's see what we have coming up next then. Example 7 is meant to be a fast concept question as well, kind of related to the other ones we were looking at. It says this time, A is this matrix. What is the dimension of the null space of A? Good call. This one has a pivot in every single column, meaning no free variables. So dimension, null space of A, 0 automatically. So that's kind of nice. We have 3 pivot columns, and so that means dimension for the column space of A equals 3. Now this said, fully justify your answer, but I mean, there's not much to really say here, right? You could say, for an example, on this one, there are 3 pivot columns. Okay, so now that one's fully justified. What about the justification on this one? You could say no free variables, or you could say determinant A is 0, which implies, well, let's see what it implies. Or excuse me, I said 0 there. Let me try again. It would really be 55. Would you all agree? That's a better determinant. Not sure. I think I was just thinking dimension for some weird reason. The determinant of A is 55. That's a good one to do over again. Glad we corrected the record on that. So what does that do for us? We go back over here to the invertible matrix theorem. And in the invertible matrix theorem, it now shows that this part and this part go together. So you could just simply say, by the invertible matrix theorem, you have dimension null space A is 0. Or, you know, honestly, maybe the better answer is you could just simply say right here, no free variables. That qualifies as well. But the invertible matrix theorem is a powerful tool. So let's say this implies dimension 0 by the invertible matrix theorem. That's the one acronym that we use over and over again in this course. Well, any last questions, folks, with those 3 quick concept style questions? Okay, so this kind of analysis that tells us dimension, call space, null space, it doesn't look like it's too major of a deal, but again, all of this is about getting into eigenvalues and eigenvectors, where these kind of ideas are going to be just par for the course, the things we have to think about. So now, finally, here's some quick applications to some of the stuff we've done here. You know, the thing that we're doing in this problem is not so much worrying about dimension as well as thinking about basis altogether. So that's the major takeaway in this problem. And that means this question is really kind of a review question in the prior section, section 4.4. It's one I assigned in the homework, so that's why we're doing it here today. I think of it as kind of just a break from thinking of dimension, but sort of, because when you're talking about bases, you're really thinking about dimension all along. But first, I should mention that the problem we're about to do is actually an honest application. It says the first four Hermite polynomials are these ones. And what in the world are those? Well, Hermite is a mathematician, and these polynomials are used in signal processing, physics, numerical analysis, numerical linear algebra, all sorts of stuff. So if you like coding, numerical math, numerical analysis, these are the things you're going to be dealing with. Hermite polynomials. In the homework question, you're dealing with the Laguerre polynomials, different but similar set of applications. And to get through this problem, pretty much this is the reminder. Working inside P3 is awfully difficult. And establishing a basis out of these things would take us, if I had to guess, I'd probably take me 30 minutes of furious writing to find out if it's a basis or not. But if we use a vector space isomorphism, then every concept in Pn is a related concept in Rn. So that's the purpose of this information here. What we need is the standard basis for P3. So let's begin by saying E, that's how we know we're dealing with the standard basis. P3 is all polynomials of degree at most 3, so it would be 1, t squared, t cubed. So this is the standard basis for P3. Sometimes it's called the canonical basis because this is just here by nature, the most natural choice that you would make for a basis. So now that we have that basis, to establish whether this is a basis or not, we begin by using the coordinate mapping. Let A be equal to, I'm just realizing we probably want some notation as well. Let's call this one P1. So polynomial 1 is the constant function. This is P2, P3, and P4. So we'll go over here and say A equals the coordinate vector of the function P1 relative to the basis E that we just put down, and then do the same thing for P through to P4. So A is going to be a matrix consisting of vectors in R4 that are the result of the coordinate mapping. Takes a moment to write that down. It's well worth it though, since we need a paper challenge, just what in the world we're doing. Anytime you use an isomorphism, that's definitely, in my opinion, some pretty wild math. So being descriptive here helps out. Okay, so now when we think of the coordinate mapping of this vector, what we're doing is applying it to this and saying, what coefficients do you have to put in front of the basis vectors in order to generate this function? Anyone see what it should be for that right coordinates? Exactly. It's kind of fun in a way, right? You're just putting in zeros on these and you get a 1 to generate that function. 1, 0, 0, 0, as you said. Same issue on this one. If you have a 2t, you have to put a 0 here to start. You have to multiply this one by 2, so 2 goes in. And because it's simply 2t, you have to wipe out these other two, so 0, 0. So that's the process. Doing this one carefully as well, because there's more going on. In order to generate this as a linear combination of those basis vectors, you need -2 times the 1. You need 0 times t, 4 times t squared, 0 times t cubed. But once you do this to get a real feel for it, you might have noticed that it's simply nothing but going over here and pulling coefficients. The coefficients of that degree 3 polynomial are 0, -12, 0, 8. So that's all the coordinate mapping is doing, pulling coefficients. That coordinate mapping is a linear transformation that's 1 to 1 and onto. And so this is an honest isomorphism. Any concept that you discuss about this matrix is a related concept about those vectors because we mapped those vectors through an isomorphism. So next thing I'd probably do is just say determinant of A equals 1 times 2 times 4 times 8, so 64, which is non-zero. Then we can take a look at the vertical matrix theorem again, but by this stage you know that if you have a non-zero determinant, you're tying together concept R with concept M. You now have a basis. The basis is just the columns of that matrix A. So let's say here, by the invertible matrix theorem, once again, the columns of A forms a basis for R4. But R4 as a vector space is completely isomorphic to P3. I should have put a 3 right here. Sorry about that. Let's put the 3 in right now. There we go. That's the actual space we're working with. So because they're isomorphic, we can conclude right here and say, therefore, B, which is equal to 1, 2t, negative 2 plus 4t squared, negative 12t plus 8t cubed, is also a basis for P3. And even though the question didn't ask for it, we can also say dimension P3 must absolutely be 4, but we knew that from right over here. That's also a basis with 4 vectors at the same time. Well, any last questions, folks, with this? I guess you could call it a review concept or question mostly. Okay, so the fact that these form basis vectors are extra special, but if you're really going to be working in, say, these kinds of places, numerical analysis in particular, what you're really doing is generating an infinite list of Hermite polynomials, more and more and more of them. You really are going to be working in not P3, but P itself, the infinite dimensional vector space. But it's good to know how this stuff goes. We really have a basis based off what we've shown here. Any questions or comments so far, folks? So to this stage? Okay, I would say we got through the main material at this point, and now we're at the point where we're looking at some of the additional concepts. If we'd like, we could explore why this is infinite dimensional. There's 3 of us in class today, so I'm going to leave it up to you folks which direction we'd like to go. If you find it might be more interesting, we could also start looking into section 5.1 to see just what we're getting into. So I'll leave it up to the class. Should we slog forward, take a look at infinite dimensional vector spaces, or start looking at eigenvalues, eigenvectors? Let's give it a try. This is a pretty good theorem. It says a couple things that are relevant to what we're looking at. It says, let H be a subspace of a finite dimensional vector space V. We're going to need that later. So now V is finite dimensional. It tells us any linearly independent set in H can be expanded if necessary to form a basis. So if you have a linearly independent set, if it doesn't span, just add another vector that keeps it linearly independent until you do have a basis. But this is the bigger punchline, in my opinion. This is, to me, the big meat of the theorem, having a finite dimensional space here, and the fact that if H is a subspace, the dimension of H has to be less than or equal to the dimension of the larger space that it's a subset of. So that makes sense in a certain sense. A subspace shouldn't have a dimension higher than the original space it came out of. So in a certain sense, it seems sensible. But here's how we're going to use theorem 11. We're going to assume that this one is finite dimensional and just see what goes wrong. What goes wrong is this right here, the space of all polynomials. Every polynomial is continuous, and every polynomial has domain, all real numbers. It's a subspace of CR. So if you assume that this is finite dimensional, but show P is a subspace, and also show P is of infinite dimension, then you have a contradiction. You can't put an infinite dimensional subspace here when V itself is finite dimensional. Let's put all those together. The hard work on this one is we have to establish P is really infinite dimensional as a vector space. Here's a weird way to argue. We will argue by contradiction. Sometimes this is called a proof by contradiction. And it's always kind of a weird technique.
That's the one where you assume temporarily the opposite is true.
Exactly. We're gonna assume this is a total lie. P is finite dimensional. So we'll make a contradiction out of that, do a little bit of math. But if we hit another contradiction, then we'll assume that reason we hit the second contradiction was because the statement we made right down here was wrong. But if it's wrong, it establishes this all along. So that's a wonderful proof technique. Some people in mathematics hate this proof technique because it's considered non-constructive. We're showing something by arguing a contradiction. We're not showing something is true by actually demonstrating its original truth. This is a really roundabout way, but it's a fast way to get at it. So let's do it this way. Assume, here's the contradiction. P is finite dimensional. Of dimension n. So we have a finite dimensional vector space. Now, if it's of dimension n, this implies immediately there is a basis for P with n vectors. There now has to be. That's the meaning of having finite dimensional. So let's write it down. Assume B equals P1, P2. These are all polynomials, so that's why we're using P to indicate them. Through, we said n vectors, so we have to end on Pn is a basis for P. Now, that's not a contradiction at all. The contradiction is right here in purple. But if we have finite dimensional on P with n vectors, or excuse me, if we have finite dimensional then, there's n vectors in a basis. So far that's not quite a contradiction, right? Except recall, these are all polynomials. And you could say, what is the degree of every single one of them? If this is function 5, its degree 0. If this is a function t cubed, its degree is 3, and so on. But there's a finite list. And so we can definitely say, let n be equal to the maximum degree among all polynomials in B. There's got to be a maximum degree. Maybe it's 50, maybe it's 5 million. Who knows? We never actually specified them. All we know is that there's n vectors there. And so there's got to be a maximum degree. Now we've got a problem. We're about to build a contradiction, so let's go back to red. If there's a maximum degree polynomial, then we can always exceed that. Let Q of t be equal to t to the power of n plus 1. This is of higher degree than every single thing inside here. And the special thing about polynomials is if you span polynomials, the degree never increases. The only way you rise the degrees of polynomials is if you do this. Now you've got x cubed, where the degree here was 2, degree was 1, but you're not allowed to do that operation. As a vector space, we can only do vector addition, that's adding polynomials together, or scalar multiplication, that's just multiplying the whole polynomial by a number. None of them have this effect. The degree never increases. So now, because this had finite degree n, and we can define a real polynomial of higher degree, we can now say this. Since Q of t is of higher degree than every vector in B, we have that. Oh, but I meant to switch colors. We have that span of P1, the vectors there inside B, through Pn is not P, Because we found one polynomial, there it is, for which the span of the set can never actually generate that polynomial. The span of the set is smaller than the space P, in other words. We now have an honest contradiction because we said there is a basis. What went wrong? Well, that can't be a basis unless it actually spans the entire set, but it's now impossible. You can demonstrate there's a polynomial there that you can never write as a result of a linear combination. So now we're at to the good stuff. We could say here for our conclusion, this contradiction shows P is not finite dimensional. I'll just say dim because I ran out of space there. Because we had a contradiction right here, and we didn't do any wrong thing in mathematics up to this point. We assumed that the problem was right there. The moment we assumed finite dimensional, we ran into problems. This must have been false, in other words. So if it's not a finite dimensional, that means the dimension of the polynomial space of any degree is infinity. So that's just re-saying what we said here. So if it's not finite dimensional, it's of infinite dimension, and that's just a shorthand for writing it in. So now what can go wrong? If we go to this space of all continuous functions, it could be, say, C, A, B as well. You could do a closed set, maybe 0, 1, 0 to 12. But the reason I put in CR is because this thing has domain R. Every polynomial has that domain. But now we have a big problem here. It says show that the space CR of continuous functions is infinite dimensional. You can argue the same way. If you assume CR is finite dimensional, well, you have a problem because P is a subspace. So you can't have dim P less than or equal to dimension of CR if this space right here was really finite dimensional. It would have to be infinite dimensional for that to work out. Or said in more simple terms, a better analogy is that you can't plug an infinite dimensional subspace inside something that's finite dimensional. So the quick argument here is that since P is a subspace of CR, and since the dimension of that vector space P is infinite dimensional, we have dimension of the space of all continuous functions with domain real numbers is infinite dimensional as well. So these are some really bizarre vector spaces. And I mention this pretty much in every class I teach, that when you're thinking about functions, that is an extremely vast landscape of things that are happening with functions. The fact that we said they're continuous, it's still an extremely rich structure of things that you have going on there. And this starts to show the hint of why that's the case. They're both of dimension infinity, but they're not isomorphic at all. We've already hinted at some continuous functions like e to the x, transcendental functions, are completely approximated by polynomials. That's the Taylor series, Maclaurin series that you deal with in Calculus 2. So there is a tremendous amount of stuff going on. And the more math you take, the more you get an appreciation that functions are just absolutely weird things to work with. You never get that feeling in college algebra, but you start to realize it in linear algebra for sure. Well, any last questions, folks, with any of the work we've done here? Okay, well, that's finally our conclusion to chapter 4. And with all that work, when we go now into dealing with eigenvectors, eigenvalues, pretty much just redoing a lot of the stuff we're doing. A very, very common calculation that we'll perform is find the null space of A minus lambda I. If you can find that, you're finding the eigenvalues written as lambda, and the basis for this is going to be the two eigenvectors that you want to work with. So we're just redoing just about everything in chapters 1, 2, 3, and 4 in chapter 5. It's a nice culminary kind of section. I don't think we can really take an honest look at it in 5 minutes though, so this would probably be a good stopping point for us. Any last questions before we call tonight officially? Okay, well, I appreciate your hard work, folks. Sorry, say again.
The last one.
I agree. It's not stuff we're gonna assess directly on any exams. I didn't even put these on the homework, but it is kind of cool to know that there is some really monstrously weird stuff out there. And the more work you take, even if you're in engineering, if you're electrical engineering, anything like that, physics, chemistry, you start to deal with this more and more and more. Things like Fourier series, it's just this kind of stuff all over again. Fourier series, you're dealing with a vector space with an inner product defined, and you're just looking at linear combinations of functions to generate other functions. So it's the same kind of stuff comes right back. Well, that's definitely all I have for the moment. When we come back next Tuesday, we'll be doing eigenvalues, eigenvectors. Well, thanks for your hard work, folks. If you have any questions, don't hesitate to stick around. I'll be happy to help.